So in this lab, we'll be looking at kinetics, which is the study of the rate of the reaction, so how fast a reaction will occur. And the important thing about kinetics is not only how fast the reaction occurs, but also understanding how the molecules or atoms are reacting. So if you were to take higher level chemistry classes, you actually go into what's called the mechanism of what atoms are reacting to give you the chemical reaction. So what we look at normally is the overall reaction. We don't look at the individual steps that make up that overall reaction. And that's called the mechanism. So it's like the steps it takes to produce those products from the reactants. And so for any chemical reaction, there are three important things that you need to have in order for a reaction to occur. And so we'll use the example of molecules. So molecules must collide, so you have to have collisions for reactions. And when molecules collide, they have to have sufficient energy, so when they collide, they react. Now, not only do they need energy, but they need orientation as well. So the molecules have to be oriented in a certain way so that when they collide with the right energy, they react. And as we'll see throughout this lecture, that even though if you have the right energy and molecules collide, if they're not oriented the right way, no reaction will occur. So you got to imagine there's millions and millions of molecules colliding, and only very few of them out of those millions and millions are what produce reactions. Now with kinetics, what we do is we monitor either the disappearance of a reactant over time or the appearance of a product over time. So in this lab that we'll be doing for this session, we'll be looking at the appearance of a product. And the appearance of the product is the blue iodine starch complex that forms that signifies the end of the reaction. And so again, over time, if we were to monitor the reactant, over time the reactant decreases because it's being consumed. And over time the product increases because it's being produced. So you can either monitor the disappearance of a reactant, or you monitor the disappearance, the appearance of a product. And in this lab, we'll be monitoring the appearance of a product. So you'll be seeing how long it takes for this iodine starch complex to form. And that's, you're going to record the amount of time it takes for it to form that product. So we want to show you what happens with kinetics as time progresses. So here we have this chemical reaction involving red molecules, and so over time we start to produce more and more white molecules, and eventually the solution may change from a red to a colorless solution, and that would indicate that all the red molecules have been consumed. So there has to be some type of way of knowing when either all the reactant is consumed or all the product or product has been produced. So we've got to look for a color change, or it could be a gas given off, etc. So that's what we're looking for when we're doing an experiment for kinetics. We're looking for how can we identify when all the reactant is consumed or product has been produced. And one of the good ways to do this is a color change. And so in this chemical reaction here, we start off with a red color solution. The reaction progresses over time and starts to turn an orange to a gold, and when it gets to colorless, means the reaction has finished. So what you would do is, if you were measuring the kinetics, you would start with some known concentration of your reactant, and then you would measure the amount of time it takes to go from this color solution to colorless solution, and you would record the time. And then you would change the concentration of the reactant, and again measure the time it takes to go from a colored solution to a colorless solution. And you do this for several experiments to get the kinetic data you need for this. So now you're going to start with a colorless solution. You're going to time how long it takes to turn a bluish, or I would say maybe violet color solution. So we're going to be timing how long it takes the reaction to produce that complex. And so when we have chemical reactions, what's happening is for the reactants, we must break bonds. For the products, we have to form bonds. So it takes this energy to break bonds, and sometimes it even takes energy to form bonds. So where does the energy come from? It comes from the collision of molecules. So molecules have to be moving at a sufficient amount of speed, so when they collide, they have enough energy to react. And this could involve breaking bonds, and then these atoms recombine into new products that have a lower energy arrangement. And so what we call for collisions that produce products is an effective collision. So that means when they collide, they have the right orientation, the right energy to have an effective collision, because not all collisions are effective. Now, one thing to notice in this chemical reaction is that you notice that the energy is listed as a product. And so whenever you see energy listed as a product, that means heat is released. And we refer to this as an exothermic reaction. So whenever you see energy, it could be in kilocalories or kilojoules. This means that energy is being released. So a good example of this is if you ever gone to you have a gas grill, you turn on the propane. The propane being combusted is a exothermic reaction. That's why your grill gets hot and cooks your food on the grill. Now, if energy was on the product side, so if you look at a chemical reaction and heat, excuse me, on the reactant side, then this would be a endothermic reaction. And so let me just give you an example of that. Say we take heat plus solid sodium chloride gives us aqueous sodium chloride. And so here heat is being absorbed because it's a reactant to dissolve the sodium chloride in solution. So whether you see heat as a product is exothermic. If you see heat as a reactant, it's endothermic. So there could be some number here, like, for example, 50 kilocalories. That indicates it's an endothermic reaction. And so with chemical reactions, we have those that release heat and those that absorb heat. And an example of an endothermic reaction is something whenever you have one of those packs that you break and it becomes cold and you put it on your muscle or your bone, that's performing an endothermic reaction. And so this energy that we talk about has a particular name. It's called the activation energy. So the activation energy is the minimum amount of energy you need to start the chemical reaction. So it's like this hump you have to overcome as the molecules collide to form the products. And so all reactions have this activation energy. And at the top of this peak, if you want to call it, of this hump, we have what's called an activated complex. And the activated complex is like the midway point between reactants and products. And so once it gets enough energy, then it rolls over the hump and it forms products. So at the maximum amount of energy is where you have this activated complex, which is, again, it's like this midpoint between bonds breaking and bonds forming to form new products. And so all chemical reactions have this activation energy. And there are things we can do to help overcome this energy barrier for chemical reactions. To give you an example, if you put, your fruit in the refrigerator, it stays fresh longer. It doesn't spoil. But if you take the fruit and you put it out on the counter where it's warmer than the refrigerator, the fruit spoils quicker than it would in the fridge. And that's because since it's hotter on your counter, it gives kind of the reaction a head start to overcome that activation energy to form the spoilage of the fruit. Whereas in the refrigerator, since it's colder, it's going to take longer for it to overcome the activation energy to form the spoilage. That's kind of like, I guess, a simple example explaining how this works for reactions. And this is how we show that the activation energy for a reaction. We use what's called an energy diagram. That's what this is. It has energy on the y-axis and reaction progress on the x. And A and B are our reactants, C and D are our products. And this hump that we have to overcome, or this peak, is the activation energy. So once you overcome this, then you roll down and form products. Now, since the products are lower in energy than the reactants, this would be an example of an exothermic reaction. So heat is released based off of this energy diagram. And so at the peak of the energy diagrams where we have that activated complex. And so again, since the products are lower than the reactants, heat is released, and this is an exothermic reaction. Now, you may ask, well, what happens when heat is absorbed? So when heat is absorbed, it's an endothermic reaction, and you notice the difference in the energy diagram. So here you notice that the reactants are lower in energy than the products. And so this means energy is absorbed to go from reactants to products, but you still have to overcome this activation energy. And so this is just more of a pictorial of what's occurring. So here we have this reaction involving a compound BrCH3 plus OH minus. And so you see at the start, we have the reactants and both reactants. Now as we start making our way up to the activated complex, we start to see the bromide leaving the carbon and the oxygen coming into the carbon. And then at the activated complex, the peak of the activation energy, we get the midway point from it. And then once it gets enough energy, it rolls downhill, the bromide leaves, and we form a carbon-oxygen bond to get the products. So this is kind of like on a molecular level, what's occurring in the different parts of the energy curve. And so this would be an exothermic reaction because the products are lower than the reactants. So besides, we talked about temperature affecting the rate of reaction. There's also a few other things that can affect the rate of reaction, such as the structure of the reacting species, of course, the molecular shape and orientation, the concentration can. So in this lab we're going to be changing the concentration of reactants and seeing how that will affect the rate of reaction. With temperature, we mentioned physical state. also plays a role. So the physical states of the reactants, whether they're gaseous, liquid, solid, or aqueous, does have an effect. And then, of course, the presence of a catalyst. So all of these different things affect the rate of reaction. Now, items 3 through 6, or 3, 4, and 6, we'll be looking at in the lab as well. So structure, so when we talk about structure, we're talking about, whether it's a charged species, and when it's oppositely charged species, they react more rapidly than if they were the same charge, because ions of the same charge don't react. Bond strength also plays a role. So of course, the weaker the bond, the easier it is for the bond to break, therefore requiring less activation energy. So if it's a stronger bond, it's going to take more energy to break it. So for example, if you have a double bond in a reactant versus a single bond, it's going to take more energy to break the double bond, hence you're going to need more activation energy than you would a single bond. So the structure of the reactants does play a part. Now with molecular shape and orientation, we prefer, smaller molecules have a better chance of collisions versus large molecules, because as we'll see in these examples, there's really only one part of the molecule that makes an effective collision. And so down here we have an example involving a chloride radical and NOCl. So when the NOCl molecule is colliding with the Cl radical, and both Cl's are pointed towards each other, we get an effective collision, and we get Cl2 and NO. But now let's say instead of the chlorine atom colliding with this chlorine, we have an oxygen, and when the oxygen collides, there's no reaction. So this would be an ineffective collision. So again, the orientation of the molecule does play a role in its collision. Now if we look at this one where we have NO and NO3, you can see all the different types of orientations of NO3 that don't give an effective collision. And then at the last one is the only one out of all 5 of these shown that gives an effective collision to form products. So say 1 out of 5 collisions leads to an effective collision. So molecular shape and orientation of the molecule is very important. So concentration does play a role with rate of reaction. So if you think about it, the greater the concentration of reactants, the more, for example, molecules of reactants you have. So the more molecules of reactants you have, the more likely that those are going to lead to effective collisions. So now you have more collisions. There's a higher probability of those collisions leading to effective collisions, rather than if you just had one collision. So for example, if we were in a room and there was only 5 of us and we started walking around with blindfolds, we wouldn't hit each other that often. But now let's say in that same room we got 100 people all with blindfolds and we start walking in random directions, we would have a better chance of colliding with a molecule or another person, because now there's more people in the room. So the same thing with molecules. The more molecules you have, the more likely you're going to collide with the other molecule. Now temperature, we kind of touched on this earlier in the lecture, but temperature also increases the rate, because what happens is when you increase the temperature, you're having a direct effect on the average kinetic energy, aka the molecule's movement. Because remember, kinetic energy is based on how fast the molecule is moving. So the more energy that that molecule has, the more likely when it collides it's going to get a effective collision. So increasing the temperature, which is kind of related to increasing the kinetic energy, helps in getting more effective collisions. Oops. Close the door. And then the physical state. So different physical states have different effects on the chemical reaction. So things like solid states, since the atoms are kind of restricted, there's less ways for those molecules to move. So for example, something in the gaseous state would have a better effect than something in the solid state. And then in the liquid state versus the gaseous state, you got to remember in liquid state molecules are closer together, so they're more likely to collide with effective collisions. Whereas in gaseous state, molecules are very far apart, and so therefore they wouldn't collide as much or have collisions as much as in the liquid state. Now, one of the last things we mentioned was a catalyst, and a catalyst is something that helps increase the rate of reaction by lowering the activation energy. So the catalyst itself is not consumed by the reaction. All it does is it helps by some alternate pathway to lower the activation energy for the reaction, making it easier to go between reactants and products. And so one of the most common catalysts that we know of is the catalytic converter on your car, which takes the poisonous exhaust gases from the motor and converts them into less poisonous gases. And that uses it by having a catalyst which accelerates that reaction. And so again, a catalyst itself is not consumed in the reaction. It just provides an alternate pathway for the reaction to occur. And so one type of catalyst is a solid phase catalyst, where you have some solid material. For example, in this reaction of forming ammonia, the gaseous nitrogen and hydrogen molecules attach to the surface of the catalyst. Again, the catalyst provides some pathway to help accelerate this reaction, in this case by weakening the bonds between the two hydrogen atoms and the two nitrogen atoms, making it easier for them to react, and then ammonia is released from it. So again, it provides an alternate means for the reaction to occur, because if this reaction was to occur without a catalyst, it would take a very long time. One catalyst that you're probably familiar of is enzymes, which are in our body, and they help catalyze reactions in our body that may otherwise take thousands, 10,000 years to complete. And so enzymes are what we call biological catalysts. They help accelerate the reactions in the body. Now, to help explain how the rate is affected by the different reactants, they have something called a rate law. And so the scope of this course is not to calculate the rate law, but just to show you what the rate law is. So the rate law relates the rate to the concentration of the reactants. And this K is what we call a rate constant. And there's ways to calculate the rate constant. Now the N and N prime that you see is how effective the reactant is at affecting the rate. And so these are usually whole numbers like 0, 1, and 2. And to give you just a brief example of this, and these numbers, by the way, are determined experimentally. Let's say we have a 1 reactant, rate equals K A to the N. Now let's say N is 0. What this tells you is that concentration doesn't affect rate. Because if A is raised to the 0 power, that means that there's no effect on concentration with the rate. And another common one is N equal 1. And what this tells you, if you doubled the concentration, then you would double the rate. So it's a one-to-one relationship. So if you double the concentration, you would record a doubling of the rate. And then if n is 2, what that means is if you double the concentration, you would quadruple the rate. And again, this is determined experimentally for different reactions. So you have to do experimental, or you have to get experimental data to solve for what this n is. And that tells you how effective that reactant is at changing the rate. And these are just some of the common numbers that we use: 0, 1, and 2. Now for the reaction we're doing in the lab is actually a 3-step process. And what happens is we start with iodide and we react it with peroxide in an acidic solution. We form the triiodide ion and water. Then what happens is the triiodide, this I3 minus, reacts with sulfur thiosulfate or thiosulfate ion. And it forms iodide and this sulfur oxoanion. And so what we're measuring is how long it takes for this reaction to complete. So again, what's going to happen is when this this thiosulfate runs out, so when the reaction is finished, what happens is we move down to step 3, and the leftover iodide starts to react with the starch to form the blue color solution. So once you see the blue color appear, that's when the reaction has finished, because all the thiosulfate has been consumed, and now it's going to start reacting with the starch. And that's you're going to time to see how long it takes for this color to appear. And so that's what we'll be doing in lab for this session.